In this lesson, we will continue to learn more advanced ways to examine the shape of a distribution, central tendency, and variability of interval and ratio variables. We will end the lesson discussing cross-tabulation of categorical variables. While histograms are important depictions of continuous data, there is another graphic that we need to learn about regarding interval and ratio variables, and that's the box plot. To understand a box plot, we need to learn its key components. The first quartile, Q1, represents the value below which 25% of the data falls, and Q1 is located at the lower end of the box. The third quartile, Q3, represents the value below which 75% of the data falls. Q3 is located at the upper end of the box. The median, also known as the second quartile, Q2, divides the dataset into two equal halves. The median is represented by a line within the box. The whiskers represent the range of the data. The minimum and maximum values are depicted as lines extending from the box. The lower whisker typically extends to the smallest value within 1.5 times the IQ or below Q1, while the upper whisker extends to the largest value within 1.5 times the IQ or above Q3. Any data points beyond the whiskers are considered outliers. The interquartile range is the range between the first quartile, Q1, and the third quartile, Q3, and is represented by the size of the box. As an example, let's create the box plot we have in the lecture notes, heart rate values for 100 patients. Once we have the data in StatCrunch, we can select box plot from the Graph tab. We use fences to identify outliers, it is clicked on by default. We can give the plot a title and label the y-axis as well. Then click Compute and StatCrunch will create the plot. So now we easily see the Q1, Q2, which is the median, and Q3. If you drag your mouse over the box, you can see all the values that StatCrunch has calculated, including the whiskers. Here the whiskers use the 55 for the lower limit and 74 for the upper limit. This is the range in which we don't have any outliers, and here it is the whole range of the data as we have no outliers. Recall that we can get these values from the Summary Statistics menu in StatCrunch, and we can also make a frequency table for this data to see all the work StatCrunch displays in the box plots. If we want to see an example of how StatCrunch handles outliers, we can add more values. Load this data into StatCrunch and remake the box plot. Now you can see that this augmented data set has some outliers in it. So here the median is 66, so the values of the quartiles and upper limits will change. The software will now identify the values of those subjects as outliers. So now we have two ways of plotting this data. A histogram and box plots display the same data in different ways. But with a box plots, you can easily identify the quartiles and all the other descriptive statistics in one graphic. The next index we will use in this course is called the standard score, or z-score. The concept of a z-score stems from the field of standardization, and through the use of z-scores, we can assess how a particular data point relates to the overall distribution and understand its relative position. In exact terms, a z-score represents the number of standard deviations a given data point deviates from the mean of its distribution. The calculation of a z-score involves two key steps. To calculate a z-score for a specific data point, subtract the mean of the distribution from that data point. This step helps determine how far the data point deviates from the average value. Here, x represents the data point, and m denotes the mean of the distribution. After subtracting the mean, divide the result by the standard deviation of the distribution. This step scales the deviation relative to the spread or variability of the data. The resulting z-score indicates how many standard deviations the data point is away from the mean. A positive z-score suggests that the data point is above the mean, while a negative z-score indicates that it is below the mean. Let's do an example from our pertussis infection rate data. We previously made a histogram of this data set and found the summary stats. Now we can determine z-scores. We can calculate this by hand from the formulas we just learned, and StatCrunch can do it too once the data is loaded in. Once we have our box plots done, we can see the outliers here. To get StatCrunch to calculate the z-scores, we have to tell it what to do. So, from the Summary Stats area, we click the Data tab, then Compute, then Expression. We are going to tell the software how to calculate the standard score by entering the formula we just learned. We need to place this formula into StatCrunch, making sure whatever we call the variable column goes in the formula. Click Compute and StatCrunch will calculate all the standard scores. So that tells us how far that data point is deviating from the average and in what direction, below the mean in the case of this first value. We will next focus on describing relationships between two variables. We will start with crosstabulation of two nominal level variables. We do that in what's called a contingency, or crosstabulation table. When creating this table, the rows represent one nominal variable, while the columns represent the other. The cells in the table display the frequency or count of observations that fall into each combination. Depending on how many groups or outcomes you have in each category, you can have multiple cells in your table. Let's start with just two groups or outcomes for each variable. In this table, we can see the counts of individuals from each gender expression category, male and female, who have a smoking preference, the smoking status category, smoker or non-smoker. From the table, we can observe that most subjects here do not smoke. We also see no difference between females and males in terms of their smoking. Analyzing crosstabulation tables involves calculating proportions or percentages within each category. It's split evenly as far as gender expression goes. There's 50 males and 50 females, or 50% each, as we have 100 total subjects, right? But we have few smokers in our sample. Next, we look to see if smoking differs by gender. Is smoking contingent upon gender? The first thing to note is that the outcome, the dependent variable, smoking status in this case, is in the rows. By convention, we always put the dependent variable in the rows. If we look at the males in the study, we see the counts. 10 males are smokers, right? We list the row percentages. 10 of all the 20 smokers here are males, so that's 50%, right? Next is the column percentage. The percentage of males who smoke. That's 10 out of 50, or 20%. Next is the total percentage, or percent of total. 10 out of all the 100 total subjects here are males who smoke, so that's 10%, right? We continue this contingency calculation for each cell. So let's do an example of people using echinacea to reduce colds. Here the ones or twos are coded categories of yes and no. We can start with the cold status and start filling in the data, as each column is a variable that we label cold status yes and no in the group they are in, which would be the sugar pill and the echinacea, or control and treatment group, respectively. So, if 7 took a sugar pill and 4 people got a cold, we have 4 yeses here and 3 nos, and we can just keep filling in the categorical data. We create the table in StatCrunch by clicking on the Stat tab, Tables, Contingency, then Data to open a dialog box to set up the table. The rows is the dependent variable, the outcome. Cold status here. The independent variable goes in the columns. That's their group. Then we're going to click on the row percent, column percent, and percent of total. Click Compute, and we have the table. To get all the labeling done properly, we copy and paste into Word and edit it there. The columns are our independent variable, the group. We just have to type in what this is and add a row above that to type in the group, treatment or control. Their cold status is in the rows, so we just type in cold status, no, yes, and then we can label the row and column percentages. This is the percentage within the dependent variable. Here it's called cold status. These were the people that did not get a cold. There was 8 of them, and 5 were in this group, so 5 divided by 8 is 62.5%. So, it's calculating all these percentages based upon what group they're in, what row, and what column they are in. This one is the column percent, or percent within group, and the last one is percent of total. And then we can just copy and paste the rest of the labels down and edit them. When finished, we have our groups of 7 each. There's our total, 14. Then, for each one, we can see the cold status of each group. So those that didn't get a cold, most of them were taking the echinacea, 62.5%, as opposed to 37.5%, and the ones that got a cold, most of them were in the sugar group. So, each of these are contingent upon the other. Here we can see that if you take echinacea, you've got a 62.5 chance of not getting cold. If you don't, you've only have a 37.5 chance of avoiding a cold. This suggests a potential association or contingency between taking echinacea and getting a cold. Let's do another example using summary data. Here we have a study comparing two procedures for removing kidney stones, either with open surgery or with percutaneous nephrolithotomy, PCNL. 87 patients had the open surgery, 81 had a successful outcome, 27 patients had PCNL, and 234 had a successful outcome. To create the table in a summary fashion, we just have to set it up a little differently in StatCrunch. So we put our independent variable in these two columns, and then our dependent variable goes in the first one. It's just like making the final StatCrunch output as a setup. So, our dependent variable here is the surgical outcome, right? Successful outcome. Our category here is yes and no. So, for the open surgery, 81 were successful and we had a total of 87 patients here, so 6 did not have a successful outcome, that's 6 no's. We had a lot more patients do the PCNL. 270 patients had the procedure, 234 were successful, 234 yeses, and then 36 did not have a successful outcome, so 36 no's go here. Now to create the table, we do the same analysis, but this time we select Summary Data. Click on the Stat tab, then Tables, then Contingency, then Summary. This opens a dialog box to set up the table. And again, we click the same things, row %, column %, and % of total, and click Compute. It did all of the percentages for us, and we just copy and paste and edit in Word as we did before. As you look at this result, the people with a successful outcome, most of them had the PCNL procedure. One is contingent upon the other. This suggests a potential association or contingency between the procedure one had and a successful outcome. Next, let's do an example of crosstabulation with a data set in Excel. We can look at the dataset for the discussion question of this module that examines risk factors of giving birth to a low-weight baby. Once you can download that dataset, you click on the codes in the Excel sheet to see what the code numbers mean. To look at a contingency table for this data, we just load the data into StatCrunch and we can do the same analysis. To construct the table, we click on the Stat tab, Tables, Contingency, and with Data, as we have all the raw data here. Our dependent variable or outcome here is whether or not they had a low birth weight baby, right? The smoking status is the independent variable, so we'll put that in the columns. Again, we'll click on row %, column %, and % of total. Click Compute, and we have our table. So, we'll just copy and paste this into Word to edit the table. Now we see the percentages. Subjects that smoked during pregnancy only had a 34% chance of having a normal weight baby. Non-smokers fared better. 66% of healthy weight babies were born to those who did not smoke. This suggests a potential association between smoking and having a normal weight baby. In summary, crosstabulation tables help us understand the contingent relationship between two nominal level variables by showing how the categories of one variable are distributed across the categories of the other. In the next lesson, we will finish our discussion of descriptive statistics by learning about correlation of two variables, another powerful technique that deals with bivariate data.